Below the twilight zone, the bathypelagic realm begins, a province of perpetual night extending down to roughly 4,000 meters. Here, sunlight has vanished entirely, and temperature stabilizes near freezing. Pressure increases with relentless precision, exceeding hundreds of atmospheres, compressing gas spaces and challenging protein stability. Organisms that inhabit this depth exhibit profound physiological specialization. Many lack swim bladders, relying instead on lipid-rich tissues or reduced skeletal mass to maintain neutral buoyancy. Metabolic rates slow, reflecting limited food availability. Predators often possess distensible jaws and expandable stomachs, adaptations suited to capturing rare, unpredictable prey. Vision is reduced or modified for detecting faint bioluminescent signals. The environment is acoustically sensitive. Low-frequency sounds propagate efficiently, carrying information across great distances. In this realm, energy is sparse and life unfolds deliberately. The bathypelagic ocean is not empty but measured, shaped by scarcity and governed by the quiet physics of compression and cold. Deeper still lies the abyssopelagic zone, stretching across the vast abyssal plains between 4 and 6 kilometers beneath the surface. Temperatures hover just above freezing, and pressure surpasses 500 atmospheres. Sediment blankets the seafloor in fine layers accumulated over millennia. Life persists, though sparsely distributed and often slow-growing. Many abyssal organisms exhibit reduced musculature and fragile bodies adapted to minimize energy expenditure. Some species produce antifreeze-like proteins that stabilize cellular structures at low temperatures. Biochemical processes operate under extreme hydrostatic pressure, requiring molecular conformations resistant to compression. Oxygen concentrations remain sufficient due to slow but continuous thermohaline circulation, sustaining aerobic metabolism. The seafloor community includes holothurians, polychaete worms, and specialized crustaceans that feed upon detritus descending from above. The abyss is characterized less by spectacle than by persistence. Its ecosystems endure on minimal inputs, shaped by sedimentation rates measured in millimeters per thousand years, embodying biological endurance within geological stillness. At the margins of tectonic plates, submarine trenches descend beyond 6,000 meters into the hadal zone, among the least explored environments on Earth. The Mariana Trench reaches depths approaching 11 kilometers, where pressure exceeds 1,000 atmospheres. Under such compression, cellular membranes and proteins risk structural failure unless uniquely adapted. Hadal organisms exhibit specialized lipid compositions that maintain membrane fluidity and enzymes modified to function under crushing forces. Amphipods, snailfish, and microbial communities persist within trench sediments, feeding on organic matter funneled downward by steep topography. Earthquakes periodically disturb these sediments, redistributing nutrients and reshaping microhabitats. Chemical gradients between pore water and overlying seawater sustain microbial metabolism. These trenches act as repositories for organic carbon and even anthropogenic debris, illustrating the reach of human influence. Yet despite remoteness and pressure, life continues to adapt. In the hadal depths, biology confronts the physical limits of compression, redefining resilience within Earth's most extreme marine frontier. Deep sea chemistry diverges from surface conditions in subtle but consequential ways. Dissolved oxygen, pH, and nutrient concentrations shift according to circulation patterns and microbial respiration. As organic matter sinks and decomposes, bacteria consume oxygen and release carbon dioxide, influencing carbonate equilibria. In regions of limited ventilation, oxygen minimum zones develop, compressing habitable depth ranges for many species. Trace metals such as iron and manganese cycle through oxidation and reduction states, mediating biological processes and sediment chemistry. Hydrothermal systems inject reduced compounds into deep waters, altering local chemistry through plume dispersion. The carbonate compensation depth marks a boundary below which calcium carbonate shells dissolve more readily than they accumulate, shaping sediment composition across basins. These chemical gradients govern distribution of organisms and long-term carbon storage. The deep ocean functions as a vast reactive reservoir, buffering atmospheric change while slowly integrating inputs from biological decay, tectonic activity, and continental weathering. Sound travels through seawater with remarkable efficiency, far surpassing its propagation in air. Temperature, salinity, and pressure collectively determine acoustic velocity, creating layers that refract and channel sound waves. One such feature, the SOFAR channel, forms at intermediate depths where sound speed reaches a minimum, allowing low-frequency signals to travel thousands of kilometers with minimal attenuation. Marine mammals exploit this property for long-distance communication, while human technologies rely upon it for submarine navigation and oceanographic measurement. Acoustic thermometry measures temperature variations across ocean basins by analyzing travel times of sound pulses. However, increasing anthropogenic noise from shipping, seismic exploration, and naval sonar alters the acoustic landscape, potentially disrupting biological communication and orientation. In the deep sea, where light is scarce, sound becomes a primary sensory medium. The ocean is therefore not silent but resonant, structured by gradients that guide acoustic energy through hidden corridors spanning continental scales. Submarine volcanoes, scattered along mid-ocean ridges and hotspot chains, continuously reshape the seafloor. Basaltic magma extrudes into cold seawater, forming pillow lavas whose rounded forms reflect rapid quenching. Over time, successive eruptions construct seamounts that may rise thousands of meters above the abyssal plain. Some eventually breach the surface, forming volcanic islands. Others remain submerged, influencing local circulation and biodiversity. Hydrothermal alteration of newly formed crust modifies mineral composition, contributing ions to seawater. Volcanic gases, including carbon dioxide and sulfur compounds, dissolve into surrounding waters, participating in chemical cycles. Seamounts create localized upwelling as currents encounter their slopes, enhancing nutrient supply and attracting pelagic species. These undersea mountains serve as biological oases amid otherwise uniform depths. Volcanism beneath the ocean is not episodic but continuous on geological timescales, silently renewing crust and altering ocean chemistry through processes concealed beneath kilometers of water. Historical shipwrecks rest across continental shelves and abyssal plains, preserved by cold temperatures and low oxygen conditions. Wooden hulls may remain intact for centuries in deep and noxic environments, while metal structures corrode slowly through electrochemical processes mediated by microbes. Notable wrecks, such as RMS Titanic in the North Atlantic, provide insight into both maritime history and deep-sea ecology. Iron-oxidizing bacteria form rustical structures that gradually consume exposed steel, integrating human artifacts into biological cycles. Sonar mapping and remotely operated vehicles have expanded underwater archaeology, revealing trade routes, naval battles, and lost cargoes. These submerged relics act as artificial reefs, attracting fish and invertebrates. They also serve as time capsules, preserving technologies and materials from past centuries. The deep ocean thus archives human endeavor, storing fragments of exploration, conflict, and commerce beneath layers of sediment and darkness. Methane hydrates accumulate within continental margin sediments where pressure and temperature stabilize crystalline structures of water encasing methane molecules. These clathrates resemble ice yet burn when ignited due to trapped gas. Vast deposits exist along continental slopes, representing significant potential energy reserves. Disturbance of hydrate stability through warming bottom waters or tectonic activity may release methane into the ocean and potentially the atmosphere, influencing greenhouse dynamics. Microbial communities metabolize methane within sediments, converting part of it to carbon dioxide and mitigating large-scale release. Geological records suggest that rapid hydrate dissociation events may have contributed to ancient climate perturbations. Extraction proposals raise concerns about slope stability and ecological disruption. Methane hydrates illustrate the ocean's role as both reservoir and regulator of carbon compounds. Beneath quiet seabeds lie structures capable of altering atmospheric chemistry if destabilized, linking sedimentary processes with planetary climate feedbacks. Polar oceans operate under seasonal extremes of light and ice cover. During winter months, extensive sea ice forms, increasing surface albedo and insulating underlying waters from atmospheric exchange. In spring, melting ice releases trapped nutrients and stratifies the surface, triggering intense phytoplankton blooms beneath retreating ice edges. Antarctic krill thrive in these conditions, forming the basis of Southern Ocean food webs that support whales, seals, and penguins. Brine rejection during ice formation increases salinity and density of surface waters, contributing to deep water formation in polar regions. These sinking waters drive components of global thermohaline circulation. Ice algal communities inhabit brine channels within sea ice, sustaining microbial ecosystems in sub-zero conditions. As climate patterns shift, alterations in ice extent influence albedo, circulation, and biological productivity. The polar seas thus function as climatic regulators, coupling cryospheric processes with oceanic circulation and atmospheric exchange in tightly interwoven cycles. The future trajectory of the oceans is shaped by chemical, thermal, and biological feedbacks unfolding over decades and centuries. Increasing atmospheric carbon dioxide dissolves into seawater, forming carbonic acid and gradually lowering pH in a process known as ocean acidification. This shift alters carbonate availability, affecting calcifying organisms such as corals and certain plankton species. Simultaneously, rising temperatures enhance stratification, potentially reducing nutrient upwelling and modifying productivity patterns. Deoxygenation expands oxygen minimum zones, compressing habitable depth ranges. Yet adaptive responses emerge. Shifts in species distribution, phenological timing, and evolutionary selection may recalibrate ecosystems. Technological observation systems, autonomous floats, satellites, deep-sea observatories, now monitor changes with unprecedented resolution. The ocean remains dynamic, capable of buffering atmospheric fluctuations, yet sensitive to sustained perturbation. Its future will reflect the interplay between geophysical inertia and biological adaptability. In contemplating what lies ahead, one encounters not inevitability but complexity, an evolving marine system shaped by physics, chemistry, life, and human agency intertwined. Oceanic gyres, immense rotating systems spanning thousands of kilometers, function as planetary engines of circulation. Driven by prevailing winds and deflected by Earth's rotation, these currents organize surface waters into vast spirals. Within their centers, convergence zones accumulate floating debris and organic matter, forming regions of relative biological scarcity yet remarkable chemical concentration. Nutrient limitation in these oligotrophic waters constrains phytoplankton productivity, rendering them deep blue and deceptively clear. Along the peripheries, however, boundary currents intensify, redistributing heat and shaping atmospheric systems above. The subtropical gyres of the Atlantic and Pacific regulate climate gradients between equator and poles, moderating seasonal contrasts. Beneath the surface, Ekman transport induces subtle vertical motion, coupling wind stress with subsurface flow. These rotating basins illustrate how atmospheric dynamics imprint themselves upon marine structure. The gyre is not merely a current but a self-organizing system, integrating wind, rotation, and basin geometry into a coherent, persistent circulation pattern. El Niño, Southern Oscillation represents one of the most influential ocean atmosphere phenomena on Earth. Originating in the equatorial Pacific, it arises from fluctuations in trade winds and sea surface temperatures. During El Niño phases, weakened winds allow warm water to migrate eastward, suppressing nutrient-rich upwelling along South American coasts. Fisheries decline as productivity diminishes and global weather patterns shift, influencing rainfall, drought, and storm frequency across continents. In contrast, La Niña intensifies upwelling and strengthens temperature gradients, often enhancing marine productivity. These oscillations unfold over interannual timescales, reverberating through agricultural systems and climate regimes worldwide. Subsurface heat content and thermocline depth play central roles in sustaining and terminating events. Through this coupled feedback loop, the tropical Pacific exerts disproportionate influence on global climate variability. El Niño exemplifies the ocean's capacity to redistribute energy across hemispheres, demonstrating how regional thermal anomalies propagate atmospheric consequences on planetary scales. Upwelling zones occur where winds and currents drive surface waters away from coastlines or equatorial regions, permitting colder, nutrient-rich water to rise from depth. Along the western margins of continents, persistent winds induce Ekman transport offshore, drawing deeper water upward to replace displaced surface layers. These regions, though geographically limited, support some of the world's most productive fisheries. Elevated concentrations of nitrates and phosphates stimulate phytoplankton blooms, initiating trophic cascades that sustain anchovies, sardines, seabirds, and marine mammals. The chemical signature of upwelled water often includes reduced oxygen and elevated carbon dioxide, reflecting decomposition processes at depth. Seasonal and climatic variability modulates upwelling intensity, linking atmospheric circulation to marine productivity. In equatorial zones, divergent surface currents similarly elevate subsurface waters. Upwelling demonstrates the ocean's vertical connectivity, revealing how processes concealed beneath the thermocline sustain vibrant ecosystems at the surface through persistent, wind-driven exchange. Ocean fronts mark boundaries between water masses of contrasting temperature or salinity, forming dynamic interfaces that concentrate biological activity. These gradients, sometimes visible from satellites as sharp color transitions, arise where currents converge or diverge. Density contrasts generate shear and turbulence, enhancing nutrient mixing and attracting plankton. Predatory fish, seabirds, and marine mammals often aggregate along these fronts, exploiting prey concentrated by physical forces. Thermal fronts can migrate seasonally, tracking atmospheric patterns and altering migratory pathways. The physical mechanisms underlying frontal formation include wind stress, tidal mixing, and mesoscale eddies. Such structures are transient yet influential, shaping ecological distribution on scales from kilometers to ocean basins. Fronts illustrate how subtle differences in temperature or salinity can generate profound biological consequences. They serve as ecological boundaries within the apparent continuity of the sea, where physical gradients translate into zones of heightened life. Mesoscale eddies, rotating water masses spanning tens to hundreds of kilometers, detach from major currents and drift across ocean basins. These swirling features, analogous to atmospheric cyclones, transport heat, salt, and nutrients laterally and vertically. Warm core eddies trap warmer, salter water within their centers, while cold core eddies elevate deeper, nutrient-rich waters toward the surface. Their lifespans may extend for months, during which they influence local productivity and redistribute biological communities. Satellite altimetry reveals their presence through subtle sea surface height anomalies. Beneath their rotating surfaces, eddies modify thermocline depth and stratification, affecting phytoplankton growth. They serve as moving laboratories where physical forcing and ecological response intertwine. Mesoscale variability underscores the ocean's dynamic complexity, revealing that circulation is not solely governed by steady currents but also by transient, energetic structures that propagate across basins with measured persistence. The biological pump operates as a vertical conveyor of carbon, linking surface photosynthesis to deep ocean storage. Phytoplankton convert inorganic carbon into organic matter, which enters food webs or aggregates into sinking particles. Zooplankton grazing and fecal pellet production accelerate descent rates, transporting carbon below the thermocline. As particles sink, microbial respiration converts part of this carbon back into dissolved forms, consuming oxygen in the process. The fraction that reaches the seafloor becomes incorporated into sediments, effectively sequestered for centuries or longer. The efficiency of this pump depends on temperature, nutrient availability, and ecosystem structure. In colder regions, slower decomposition enhances carbon export to depth. Variability in the biological pump influences atmospheric carbon dioxide concentrations, integrating marine ecology with global climate regulation. Through continuous yet invisible flux, the ocean mediates exchanges between biosphere and atmosphere, modulating greenhouse dynamics through microscopic transformations. Deep scattering layers, detectable by sonar, represent dense aggregations of mesopelagic organisms that reflect acoustic signals. First identified during naval surveys, these layers migrate vertically each day, ascending at dusk and descending at dawn. Composed largely of small fish, crustaceans, and gelatinous organisms, they form a coherent acoustic horizon hundreds of meters below the surface. This diel migration constitutes a massive transfer of biomass, redistributing nutrients between depth and surface waters. The vertical displacement modifies predator-prey interactions and influences carbon cycling through respiration and excretion at depth. The scattering layer reveals the ocean's hidden dynamism, where organisms collectively respond to light cues in synchronized movement. Its discovery transformed understanding of mid-water ecology, demonstrating that the mesopelagic zone contains far greater biomass than once assumed. Beneath calm surfaces, entire communities oscillate daily, guided by circadian rhythms and evolutionary pressure. Oxygen minimum zones develop where microbial respiration outpaces physical ventilation, reducing dissolved oxygen to low concentrations. Typically occurring at intermediate depths, these zones expand in regions of high surface productivity combined with sluggish circulation. Organisms inhabiting such environments exhibit specialized adaptations, including hemoglobin variants with high oxygen affinity or metabolic pathways tolerant of hypoxia. Some microbes utilize nitrate instead of oxygen in respiration, producing nitrous oxide as a byproduct. Expansion of oxygen minimum zones has been linked to warming-induced stratification, which restricts mixing. The compression of habitable depth ranges forces species redistribution and alters food web interactions. These zones demonstrate the sensitivity of marine ecosystems to subtle shifts in circulation and productivity. Though invisible from above, their presence reshapes ecological boundaries within the water column, reflecting the delicate balance between biological consumption and physical renewal. Deep-sea corals, unlike their tropical counterparts, thrive in cold, dark waters along continental slopes and seamounts. Lacking symbiotic algae, they rely entirely on capturing plankton and organic particles from passing currents. Their calcium carbonate skeletons form intricate branching structures that provide habitat for invertebrates and fish. Growth rates are slow, often measured in millimeters per year, resulting in colonies that may persist for centuries. These corals are sensitive to ocean acidification, as reduced carbonate saturation impedes skeletal formation. Fishing practices such as bottom trawling can devastate centuries of growth in moments, highlighting their vulnerability. Deep-sea coral ecosystems reveal that reef-building processes are not confined to sunlit shallows. Even in darkness, structural complexity emerges through gradual accretion, shaping biodiversity hotspots along submerged topography. Subduction zones, where one tectonic plate descends beneath another, generate seismic and volcanic activity that influences ocean structure. Earthquakes displace vast volumes of water, occasionally triggering tsunamis that propagate across entire ocean basins. These long-wavelength waves travel at high velocities in deep water, slowing and amplifying as they approach shallow coastlines. The physical mechanism involves displacement of the seafloor, transferring energy directly into the water column. Tsunamis illustrate how tectonic forces beneath the ocean surface can reshape coastal landscapes within hours. Subduction also drives arc volcanism and hydrothermal vent formation, linking deep earth processes with marine chemistry. The ocean floor is not static but tectonically active, continuously recycled through plate motion. In these boundary zones, geology and oceanography converge, reminding us that the sea rests atop a dynamic crust shaped by forces operating over millions of years yet capable of sudden, transformative release. Submarine canyons carve deep incisions into continental margins, extending from shallow shelves down the continental slope toward abyssal plains. Often comparable in scale to terrestrial river valleys, these features are sculpted by turbidity currents, dense, sediment-laden flows that cascade downslope under gravity. Triggered by storms, earthquakes, or sediment overload, turbidity currents accelerate through canyon channels, transporting sand and organic material into the deep sea. Over geological time, repeated events excavate sinuous pathways that funnel nutrients and detritus into deeper basins. These canyons enhance biodiversity by concentrating food resources along their walls and floors. Cold-water corals, sponges, and fish aggregate in these structurally complex habitats. Acoustic mapping has revealed intricate branching networks invisible from the surface. Submarine canyons demonstrate that erosional forces operate vigorously beneath the ocean, reshaping continental margins through episodic yet powerful sedimentary flows that connect coastal systems with the abyss. Turbidity currents themselves represent one of the most energetic sediment transport mechanisms on the planet. When suspended particles increase water density sufficiently, gravitational instability drives rapid downslope movement. These currents can travel hundreds of kilometers along the seafloor, carving channels and depositing graded sediment layers known as turbidites. Within minutes, massive volumes of sediment may be displaced, burying benthic communities and reshaping submarine landscapes. Instrumented cables have recorded astonishing velocities exceeding tens of kilometers per hour. As the current decelerates, heavier particles settle first, followed by finer silts and clays, creating characteristic stratified deposits preserved in geological records. Turbidites provide evidence of past seismic activity and continental erosion. Through these episodic avalanches, continents gradually export their weathered material into ocean basins. The deep sea thus archives catastrophic events in layered sediments, each bed a silent record of gravity-driven motion along submerged slopes. The carbonate compensation depth marks a critical chemical boundary within the ocean, below which calcium carbonate dissolves more readily than it accumulates. Above this depth, shells of foraminifera and coccolithophores settle onto the seafloor and contribute to calcareous sediments. Beneath it, increased pressure and elevated carbon dioxide concentrations enhance dissolution, preventing long-term preservation. The position of this boundary varies across basins depending on temperature, circulation, and productivity. Shifts in its depth over geological time reflect changes in global carbon cycles and ocean chemistry. As atmospheric carbon dioxide rises and seawater becomes more acidic, the carbonate compensation depth may shoal, altering sediment composition across vast areas. This boundary exemplifies the intimate connection between surface processes and abyssal chemistry. Through dissolution and precipitation equilibria, the ocean regulates mineral stability, encoding climatic history within microscopic skeletal remains dispersed across the seafloor. Manganese nodules rest upon abyssal plains as dark, rounded concretions formed through extraordinarily slow chemical precipitation. Layer upon layer of manganese and iron oxides accumulate around small nuclei, shark teeth, shell fragments, or rock chips over millions of years. Growth rates may measure only millimeters per million years, reflecting gradual redox reactions in oxygenated deep waters. These nodules contain trace metals such as nickel, cobalt, and copper, attracting industrial interest. Yet their ecological context remains delicate. Benthic organisms inhabit the spaces between nodules, and sediment disturbance could persist for centuries. The formation of nodules depends on a balance between metal supply, sedimentation rate, and oxygen availability. They represent geochemical patience, sculpted by diffusion and precipitation rather than rapid tectonic upheaval. Across the abyssal plains, these scattered mineral spheres testify to the slow choreography of deep-sea chemistry operating far from sunlight and surface turbulence. Brine pools accumulate in certain deep basins where hypersaline water, denser than surrounding seawater, settles into depressions on the seafloor. Formed through dissolution of ancient evaporite deposits or salt tectonics, these pools create sharply defined boundaries that resemble underwater lakes. The interface between normal seawater and brine forms a halocline so abrupt that remotely operated vehicles observe rippling distortions akin to surface reflections. Within the brine, oxygen may be scarce, and specialized microbial communities metabolize sulfur compounds under extreme salinity. Some brine pools emit methane and support chemosynthetic ecosystems similar to hydrothermal vents. The chemical stratification within these basins illustrates how density contrasts maintain separation even in dynamic ocean environments. Brine pools are isolated laboratories of extremophilic life, revealing metabolic pathways adapted to salinity levels intolerable to most marine organisms. Iceberg calving from polar glaciers introduces massive freshwater inputs into the ocean, altering salinity and stratification. As glaciers fracture, towering blocks detach and drift into surrounding seas, gradually melting over months or years. Beneath the surface, most of the iceberg's mass remains hidden, sculpted by differential melting and wave erosion. Freshwater release influences local circulation, potentially inhibiting deep water formation if stratification intensifies. Icebergs also transport entrained sediments and nutrients from terrestrial sources, redistributing them across marine environments. In polar ecosystems, meltwater plumes can stimulate localized phytoplankton growth by stabilizing the surface layer. Over geological time, episodes of massive iceberg discharge have disrupted thermohaline circulation, leaving imprints in sediment cores as layers of ice-rafted debris. Iceberg dynamics illustrate the intimate coupling between cryosphere and ocean, where frozen continental reservoirs interact with saline basins in evolving climatic exchange. Oceanic anoxic events punctuate geological history as intervals when vast portions of the ocean became depleted in oxygen. These events, recorded in black shale deposits rich in organic carbon, often coincided with volcanic activity and elevated greenhouse conditions. Increased nutrient runoff and stratification may have enhanced productivity and subsequent decomposition, consuming dissolved oxygen at depth. Anoxic waters altered marine ecosystems profoundly, favoring organisms tolerant of low oxygen while precipitating extinctions among others. Sulfide accumulation in certain regions further stressed aerobic life. The geological record of these events informs contemporary concerns about expanding oxygen minimum zones. Anoxic intervals reveal the ocean's sensitivity to climatic and tectonic forcing, demonstrating that chemical equilibria can shift dramatically under sustained perturbation. The sediments preserving these episodes function as archives of planetary imbalance, chronicling past transformations in oceanic redox structure. Seamount chains, formed by tectonic hotspots or ridge volcanism, rise from the deep ocean floor as submerged mountains. As currents encounter these elevations, they are deflected upward, generating localized upwelling and enhanced nutrient availability. This physical forcing attracts plankton, fish, and apex predators, creating biodiversity hotspots in otherwise nutrient-poor regions. Many seamount species exhibit limited geographic ranges, evolving in relative isolation. Coral gardens and sponge assemblages colonize rocky slopes, benefiting from steady current flow. The topographic complexity modifies circulation patterns, forming eddies and retention zones that concentrate larvae. Yet seamount ecosystems remain vulnerable to deep-sea fishing and mineral exploration. Their geological origins link mantle processes with marine biodiversity, illustrating how solid Earth dynamics sculpt biological opportunity within the water column. Submarine groundwater discharge introduces fresh water and dissolved constituents into coastal oceans through permeable sediments. Though less visible than river outflow, this process can contribute significant nutrient fluxes to nearshore environments. Driven by hydraulic gradients and tidal pumping, groundwater seeps carry nitrogen, phosphorus, and trace metals derived from terrestrial sources. These inputs may stimulate localized productivity or, when excessive, promote harmful algal blooms. Chemical tracers such as radium isotopes reveal the spatial extent of discharge plumes. Submarine groundwater exchange underscores the porous nature of coastal boundaries, where terrestrial aquifers interact continuously with marine systems. The interface between land and sea is therefore not confined to visible shorelines but extends beneath sediments in dynamic hydrological exchange. Ocean color, as observed from satellites, provides insight into biological and chemical processes occurring at the surface. Variations in spectral reflectance reveal concentrations of chlorophyll and suspended particles, enabling estimation of phytoplankton biomass across global scales. Algorithms translate subtle shifts in blue and green wavelengths into maps of productivity. Changes in ocean color over time reflect climate-driven alterations in stratification, nutrient supply, and ecosystem composition. Remote sensing has transformed oceanography, permitting synoptic observation of vast basins once accessible only through ships. Beneath the tranquil appearance of blue expanses lies a mosaic of biological gradients detectable through optical physics. Ocean color integrates light absorption, scattering, and biological pigmentation into a planetary signal, linking electromagnetic radiation from the sun with microscopic life suspended in the sea. Coastal estuaries form where riverine freshwater meets saline ocean, creating dynamic gradients of salinity, turbidity, and nutrient concentration. These transitional environments are among the most productive ecosystems on Earth. Stratification often develops as lighter freshwater overlies denser seawater, though tidal mixing can homogenize the column depending on basin geometry. Suspended sediments carried by rivers settle as flow velocity decreases, forming mudflats and marshes that buffer coastlines from erosion. Nutrient enrichment stimulates phytoplankton growth, supporting shellfish, crustaceans, and juvenile fish that depend on sheltered conditions. Estuaries also function as biogeochemical filters, transforming and retaining contaminants before they reach open waters. Microbial communities mediate nitrogen cycling through nitrification and denitrification, regulating nutrient export. These environments are sensitive to upstream land use and hydrological alteration. Within estuarine waters, terrestrial and marine systems merge in fluctuating equilibrium, shaped by tides, runoff, and sediment transport in continuous exchange. The global thermohaline circulation operates as a planetary-scale conveyor, redistributing heat and dissolved constituents through interconnected basins. Initiated primarily in high-latitude regions where surface waters cool and increase in density, this circulation sinks and spreads through the deep ocean. In the North Atlantic, dense water formation drives southward flow along the abyssal floor, eventually upwelling in other regions over centuries. This slow overturning integrates temperature and salinity gradients into coherent global motion. It regulates climate by transporting equatorial heat poleward and influences carbon storage by ventilating deep reservoirs. Variability in freshwater input, particularly from melting ice, may modulate its strength. Paleoceanographic evidence indicates that abrupt disruptions in this circulation have coincided with rapid climatic shifts. The thermohaline system exemplifies the ocean's inertia, vast, gradual, yet climatically decisive. Through density-driven descent and distant resurfacing, it binds polar processes with tropical stability in a single, continuous circulation loop. Marine viruses, though invisible without microscopy, represent the most abundant biological entities in the ocean. They infect bacteria, archaea, and eukaryotic plankton, shaping microbial population dynamics and nutrient cycling. Viral lysis releases cellular contents back into the dissolved organic pool, fueling microbial loops and altering carbon flow. This process, known as the viral shunt, redirects energy from higher trophic levels toward microbial respiration. Genetic exchange mediated by viruses influences evolutionary pathways, transferring genes across lineages. Viral activity responds to environmental conditions, fluctuating with host abundance and temperature. Though individually minute, collectively they exert substantial control over ecosystem structure and biogeochemical flux. In the vast expanse of seawater, viral particles outnumber stars in the observable universe. Their presence underscores the microbial foundation of marine systems, where ecological balance depends on interactions occurring at nanoscopic scales yet reverberating across global carbon cycles. Chemosynthetic communities at cold seeps flourish where hydrocarbons and sulfide-rich fluids leak from sediments into overlying waters. Unlike hydrothermal vents, these seeps are not driven by volcanic heat but by gradual migration of methane and other reduced compounds. Microbial consortia oxidize methane anaerobically, often in partnership with sulfate-reducing bacteria. This metabolism sustains dense assemblages of clams, mussels, and tube worms harboring symbiotic bacteria. Carbonates precipitate from chemical reactions at seep sites, forming authigenic rock structures. These habitats persist for centuries, dependent on continuous chemical flux from below. Cold seeps demonstrate that biological productivity can arise independently of sunlight, fueled instead by geochemical energy gradients. They expand the conceptual boundaries of habitable environments, illustrating how life exploits chemical disequilibrium wherever it persists beneath the seafloor. Ocean acidification alters carbonate chemistry through incremental increases in dissolved carbon dioxide. As CO2 reacts with seawater, it forms carbonic acid, which dissociates into bicarbonate and hydrogen ions, lowering pH. Increased hydrogen ion concentration reduces availability of carbonate ions required for calcification. Organisms constructing calcium carbonate shells or skeletons may experience reduced growth rates or structural fragility. Regional variation in buffering capacity influences vulnerability, with polar waters particularly sensitive due to lower carbonate saturation. Laboratory and field observations reveal species-specific responses, including physiological acclimation in some taxa. Acidification operates gradually yet persistently, reshaping marine chemistry over decades. Its trajectory reflects atmospheric emissions and oceanic uptake dynamics. The phenomenon exemplifies the ocean's role as carbon sink, absorbing anthropogenic inputs while undergoing subtle yet consequential chemical transformation. Plastic debris has become an emergent component of oceanic systems, fragmenting into microplastics that disperse across surface waters and sediments. These particles originate from terrestrial waste streams and maritime sources, transported by currents into convergence zones within gyres. Microplastics interact with planktonic organisms, sometimes ingested and incorporated into food webs. They can adsorb hydrophobic contaminants, altering chemical exposure pathways for marine life. Deep-sea sediments have revealed microplastic accumulation even in remote trenches, demonstrating extensive dispersal. The persistence of synthetic polymers in marine environments reflects resistance to biodegradation. Their ecological consequences remain under investigation, encompassing physical obstruction, chemical leaching, and potential trophic transfer. Plastic presence illustrates how anthropogenic materials integrate into natural cycles, becoming embedded within oceanographic processes. Marine heat waves, characterized by prolonged periods of anomalously high sea surface temperatures, have increased in frequency and intensity. These events disrupt stratification patterns, alter species distributions, and trigger coral bleaching episodes. Elevated temperatures can reduce dissolved oxygen solubility and enhance metabolic demand, stressing marine organisms. Fisheries may experience shifts in stock availability as species migrate toward cooler waters. Heat waves often arise from persistent atmospheric blocking patterns that reduce wind-driven mixing. Their impacts cascade through ecosystems, affecting productivity and predator-prey relationships. Monitoring through satellite observation enables detection and trend analysis. Marine heat waves exemplify the ocean's responsiveness to atmospheric variability, translating transient climatic anomalies into ecological consequences. Deep ocean sediments serve as repositories of climatic history, accumulating microfossils and isotopic signatures over millions of years. Foraminiferal shells incorporate oxygen isotopes reflective of ambient temperature and ice volume. By analyzing sediment cores extracted from the seafloor, scientists reconstruct past ocean temperatures and circulation patterns. Variations in carbon isotopes reveal shifts in productivity and carbon cycling. Magnetic signatures within sediments document reversals of Earth's geomagnetic field. These stratified records provide high-resolution chronologies of glacial-interglacial cycles. Sediment archives illustrate the ocean's role as climate historian, preserving molecular and mineralogical evidence of planetary transformation. Hydrogen sulfide plumes generated in anoxic basins occasionally rise into oxygenated waters, altering chemical gradients. Such events may follow stratification breakdown or mixing episodes. Sulfide toxicity poses challenges to aerobic organisms, yet certain bacteria exploit these compounds for energy. The interplay between redox boundaries shapes microbial diversity and sediment chemistry. In restricted basins such as the Black Sea, stable anoxic layers persist below haloclines, maintaining distinct chemical regimes. These environments demonstrate how stratification governs vertical chemical separation, influencing habitability across depth. The abyssal seafloor hosts polymetallic crusts along exposed rock surfaces, particularly on seamounts. Unlike nodules formed on sediment, these crusts precipitate directly onto hard substrates. Enriched in cobalt and rare earth elements, they accumulate through slow hydrogenetic processes over tens of millions of years. Biological colonization occurs simultaneously, integrating mineral surfaces with living communities. Interest in resource extraction raises concerns regarding disturbance of long-lived ecosystems. These crusts reflect the coupling of seawater chemistry with geological substrate, illustrating gradual mineral deposition across geological time. Biological nitrogen fixation in the ocean is performed by specialized microorganisms capable of converting inert atmospheric nitrogen dissolved in seawater into bioavailable forms. Diazotrophic cyanobacteria, particularly in warm oligotrophic regions, utilize the enzyme nitrogenase to reduce N2 into ammonia, despite the substantial energetic cost. This process introduces new reactive nitrogen into surface ecosystems where nutrient limitation would otherwise constrain productivity. Iron availability often regulates fixation rates, linking trace metal supply to primary production. The fixed nitrogen supports phytoplankton growth, cascading upward through trophic levels. Without this microbial intervention, large expanses of subtropical gyres would remain even more biologically sparse. Nitrogen fixation represents a biochemical gateway, transforming chemically stable gas into the molecular architecture of proteins and nucleic acids. Through enzymatic precision, microscopic organisms modulate planetary nutrient budgets, sustaining productivity across waters that appear deceptively barren from above. Marine snow aggregates occasionally coalesce into larger mucilaginous formations known as marine gels, composed of polysaccharides secreted by plankton. These transparent exopolymeric particles bind detritus, bacteria, and minerals into suspended matrices that alter water column structure. During bloom events, extensive gel formation can reduce water clarity and influence oxygen dynamics as decomposition proceeds. These organic networks serve as microhabitats, concentrating microbial life within gelatinous scaffolds. The physicochemical properties of gels affect sinking velocity and carbon export efficiency. In some coastal systems, large-scale mucilage events have disrupted fisheries and altered benthic communities. Marine gels illustrate the ocean's capacity for self-organization at microscopic scales, where biological exudates transform dispersed particles into cohesive structures with ecological consequence. Phytoplankton diversity encompasses diatoms, dinoflagellates, coccolithophores, and cyanobacteria, each possessing distinct physiological strategies. Diatoms construct silica frustules, flourishing in nutrient-rich waters where silicate is abundant. Coccolithophores precipitate calcium carbonate plates, contributing to both carbon fixation and sediment formation. Dinoflagellates exhibit motility and, in some species, bioluminescence or toxin production. Community composition shifts with temperature, stratification, and nutrient ratios, influencing food web structure and carbon cycling. Harmful algal blooms arise when certain taxa proliferate excessively, producing toxins that accumulate in shellfish and affect higher trophic levels. Phytoplankton assemblages therefore function as both foundation and regulator of marine ecosystems. Their taxonomic balance determines pathways of energy transfer and biogeochemical flux. The mesopelagic zone harbors lanternfish, among the most abundant vertebrates on Earth. Equipped with photophores arranged in species-specific patterns, they generate controlled bioluminescent signals. These emissions may serve for counterillumination camouflage, species recognition, or schooling coordination. Lanternfish undertake nightly vertical migrations, ascending hundreds of meters to feed on zooplankton before retreating to depth at dawn. Their biomass constitutes a substantial component of global carbon transport, as feeding near the surface and respiring at depth transfers organic carbon downward. Despite their abundance, mesopelagic ecosystems remain underexplored due to sampling challenges. Lanternfish exemplify adaptation to dim environments, where light is generated biologically rather than received from the sun. Ocean alkalinity functions as a buffering capacity against acidification, determined primarily by concentrations of bicarbonate and carbonate ions. Weathering of continental rocks delivers alkaline constituents via rivers, replenishing oceanic reserves. Variations in alkalinity influence carbon dioxide absorption efficiency and carbonate saturation states. Long-term geological processes, including silicate weathering and volcanic degassing, modulate global alkalinity over millions of years. Anthropogenic carbon input perturbs this equilibrium on much shorter timescales. Understanding alkalinity distribution is essential for predicting future carbonate chemistry and calcification potential. Through chemical buffering, the ocean moderates atmospheric change while undergoing gradual compositional shifts. Submarine landslides occur when sediment accumulations on continental slopes become gravitationally unstable. Triggered by earthquakes or rapid sediment loading, these failures can displace vast volumes of material downslope. The resulting mass movements reshape seafloor topography and may generate tsunamis if sufficient water is displaced. Depositional lobes at slope bases record past slide events in layered sediments. These processes demonstrate that continental margins remain dynamically active. The interaction between sediment supply, tectonics, and slope stability governs the frequency of such events. Submarine landslides link geological forces with oceanographic consequences, occasionally producing rapid surface disturbances from deep-seated instability. Ocean circulation influences atmospheric carbon uptake through solubility and biological pumps. Cold waters absorb carbon dioxide more readily than warm waters, enhancing uptake in high latitudes. When these waters sink, they sequester carbon in deep reservoirs for centuries. Surface warming reduces solubility, potentially limiting future absorption capacity. Stratification may further inhibit vertical mixing, altering exchange efficiency. The balance between physical uptake and biological fixation determines overall sequestration rates. Circulation patterns thus regulate the ocean's role as climate stabilizer. Changes in temperature and salinity distribution reverberate through carbon storage pathways. The deep biosphere extends beneath the seafloor into sediment and basaltic crust, where microbial life persists kilometers below the ocean floor. These organisms metabolize slowly, utilizing chemical energy derived from rock-water interactions. Hydrogen, methane, and reduced minerals sustain subsurface communities independent of surface photosynthesis. Cell densities decline with depth, yet viability persists over geological timescales. The deep biosphere expands the known limits of life, suggesting that habitable zones may exist beneath planetary surfaces elsewhere in the solar system. Marine sediments thus host not only deposited organic matter but active microbial ecosystems operating under extreme energy limitation. Salinity stratification in semi-enclosed basins such as the Mediterranean produces distinctive circulation regimes. Evaporation exceeds precipitation, increasing surface salinity and promoting dense water formation. This dense water sinks and flows outward through connecting straits, while fresher Atlantic water enters at the surface. Such exchange maintains chemical balance while generating intermediate water masses that influence adjacent basins. Basin geometry and climatic forcing shape these circulation patterns. Semi-enclosed seas demonstrate how regional hydrology and evaporation rates modify broader ocean dynamics. Ocean observation technologies now include autonomous Argo floats that profile temperature and salinity to depths of 2,000 meters. Drifting with currents, these instruments periodically ascend to transmit data via satellite, constructing a global dataset of unprecedented resolution. Long-term monitoring reveals trends in heat content, stratification, and circulation variability. Complementary deep-sea observatories provide continuous measurements of seismic, chemical, and biological parameters. Through these networks, the ocean transitions from sparsely sampled frontier to continuously observed system. Technological expansion enhances predictive capacity while revealing complexity previously unresolved. Sea ice formation initiates a cascade of physical and chemical transformations in polar oceans. As surface water cools to its freezing point, crystalline structures exclude salt, concentrating brine within channels that drain into surrounding seawater. This process, known as brine rejection, increases local salinity and density, promoting vertical convection. The sinking of dense water contributes to deep water formation, a fundamental driver of global thermohaline circulation. Within the ice matrix, microbial communities colonize liquid brine inclusions, sustaining metabolic activity in sub-zero conditions. Seasonal melt reverses density gradients, stabilizing surface layers and stimulating phytoplankton blooms beneath retreating ice margins. The annual rhythm of freezing and thawing modulates heat exchange between ocean and atmosphere, influencing albedo and climate feedbacks. Sea ice thus functions not merely as frozen surface cover but as an active regulator of circulation, chemistry, and biological productivity in high-latitude seas. Antarctic bottom water represents one of the densest water masses in the global ocean. Formed along Antarctic continental margins where intense cooling and brine rejection occur, this water sinks to abyssal depths and spreads northward across ocean basins. Its movement ventilates deep waters, replenishing oxygen supplies far from polar origins. Temperature and salinity signatures allow tracing of its pathways through hydrographic measurements. Variations in its formation rate influence deep ocean heat storage and circulation strength. Paleoceanographic records suggest that shifts in Antarctic bottom water production have accompanied major climatic transitions. This dense outflow illustrates the disproportionate influence of polar processes on global ocean structure. Through gradual descent and basin-wide propagation, it integrates cryospheric dynamics with abyssal renewal. Sargassum mats drifting in subtropical Atlantic waters create floating ecosystems within otherwise nutrient-poor gyres. These brown macroalgae aggregate into extensive rafts that provide habitat for fish, crustaceans, and invertebrates adapted to pelagic life. Unlike rooted seaweeds, sargassum remains buoyant through gas-filled bladders. Seasonal and climatic variability influence bloom intensity and geographic distribution. Recent expansions of sargassum belts have been linked to altered nutrient inputs and ocean circulation shifts. When these mats strand along coastlines, decomposition can affect local economies and ecosystems. Offshore, however, they function as mobile nurseries, supporting juvenile marine species. Sargassum demonstrates how structure and shelter can arise even in open ocean environments dominated by oligotrophic waters. Oceanic dissolved organic carbon constitutes one of the largest active carbon reservoirs on Earth. Composed of complex mixtures of degraded biological molecules, this pool persists for centuries in deep waters. Microbial communities slowly transform labile fractions, while more recalcitrant compounds resist rapid decomposition. The balance between production and remineralization governs long-term carbon storage. Circulation redistributes dissolved carbon globally, linking surface productivity with abyssal chemistry. Understanding its molecular composition remains an ongoing scientific challenge due to chemical complexity. This dissolved reservoir exemplifies the ocean's capacity to store carbon in forms not immediately visible as biomass or sediment. Marine snow descending through the mesopelagic zone encounters microbial colonization that alters its chemical composition. Bacteria attach to particles, secreting enzymes that hydrolyze complex polymers into utilizable substrates. This transformation releases dissolved nutrients into surrounding water, sustaining microbial loops. The rate of degradation influences how much carbon ultimately reaches the seafloor. Temperature, oxygen concentration, and community structure modulate remineralization efficiency. Through continuous microbial mediation, particulate matter becomes dissolved carbon or atmospheric return via respiration. The fate of sinking particles determines the strength of the biological pump and the ocean's climate regulation capacity. Hydroacoustic monitoring reveals that whale vocalizations traverse ocean basins through the SOFAR channel with minimal attenuation. Blue whale calls, low in frequency, can propagate thousands of kilometers, facilitating communication across vast distances. Acoustic properties of seawater allow efficient transmission under specific temperature and pressure gradients. Anthropogenic noise increasingly overlaps with these frequency bands, potentially masking biological signals. Marine mammals rely on acoustic cues for navigation, foraging, and social interaction. The ocean's acoustic landscape therefore represents both natural communication medium and domain of emerging human impact. Ocean deoxygenation progresses as warming reduces oxygen solubility and stratification limits ventilation. Long-term observational records indicate declining dissolved oxygen concentrations in multiple basins. Expanding hypoxic zones compress viable habitat for aerobic organisms and alter nitrogen cycling pathways. Microbial denitrification may increase, influencing greenhouse gas production. Species distribution shifts reflect sensitivity to oxygen thresholds. Deoxygenation exemplifies interconnected climate and biogeochemical feedbacks unfolding over decadal scales. Phosphorus cycling in the ocean involves complex interactions between biological uptake, remineralization, and sediment burial. Riverine input supplies phosphate, which phytoplankton incorporate into organic molecules. Upon decomposition, phosphate regenerates, sustaining productivity. In oxygen-poor sediments, release of phosphorus back into overlying water may occur, amplifying nutrient availability. Long-term burial removes phosphorus from active cycling, influencing productivity over geological timescales. This nutrient dynamic shapes ecosystem structure and primary production capacity. Submarine hydrothermal plumes disperse trace metals across ocean basins. As vent fluids mix with seawater, iron precipitates yet remains partially stabilized by organic ligands. These micronutrients travel considerable distances, fertilizing surface waters when upwelled. Hydrothermal contributions to global iron budgets have reshaped understanding of nutrient supply pathways. The coupling of tectonic activity with biological productivity illustrates interdisciplinary integration between geology and marine ecology. The Mariana Trench Challenger Deep remains the deepest surveyed point in the global ocean. Exploration using crewed and autonomous vehicles has revealed microbial life and amphipods inhabiting sediments at extreme pressure. Temperature remains near freezing despite crushing compression. Plastic debris has been documented even at these depths, demonstrating pervasive anthropogenic reach. The trench symbolizes both the limits of exploration and the resilience of life under maximal hydrostatic stress. Sea level rise represents one of the most measurable expressions of oceanic change. Thermal expansion, driven by increasing heat content, causes seawater to occupy greater volume even in the absence of additional mass. Concurrently, melting glaciers and ice sheets contribute freshwater input, elevating global mean sea level further. Regional variability emerges from gravitational adjustments, ocean circulation shifts, and vertical land motion. Satellite altimetry now tracks millimeter-scale changes with remarkable precision, revealing accelerating trends over recent decades. Coastal geomorphology responds through shoreline retreat, wetland migration, and saltwater intrusion into aquifers. Low-lying island nations confront existential risk, while deltaic systems experience altered sediment dynamics. Sea level rise integrates atmospheric warming, cryospheric melt, and ocean heat storage into a single, observable metric. It reflects the ocean's role as both absorber and amplifier of climatic energy, translating diffuse thermal imbalance into tangible geographic transformation. Thermal expansion coefficients vary with temperature and salinity, meaning warmer surface waters expand more readily than colder abyssal masses. This differential response alters density gradients and potentially influences stratification strength. As surface layers warm disproportionately, vertical mixing may weaken, reinforcing separation between nutrient-rich depths and illuminated waters. Feedback mechanisms emerge. Reduced mixing limits heat redistribution downward, concentrating warming near the surface. Meanwhile, expanding water columns subtly modify pressure fields and circulation pathways. Thermal expansion exemplifies how molecular agitation scales upward into planetary geometry. The vibrational energy of countless water molecules collectively reshapes coastlines and bathymetric reference levels. Through physical law alone, the ocean converts absorbed radiation into volumetric adjustment, demonstrating the profound cumulative consequence of incremental temperature change. Marine biodiversity hotspots cluster along coral reefs, seamounts, and productive upwelling margins. These regions support disproportionate species richness relative to surrounding waters. Structural complexity, nutrient supply, and hydrodynamic variability interact to create ecological niches. Genetic diversity within such hotspots enhances adaptive capacity under environmental stress. Conservation strategies increasingly prioritize these areas for protection, recognizing their role in sustaining regional fisheries and ecosystem services. Biodiversity distribution reflects both present conditions and historical connectivity shaped by circulation. In these concentrated zones of life, evolutionary processes unfold within the fluid architecture of currents and temperature gradients. Ocean acidification interacts synergistically with warming and deoxygenation, producing compound stressors for marine organisms. Calcifying species confront reduced carbonate availability while elevated temperatures increase metabolic demand. Hypoxic conditions further constrain physiological tolerance. Multi-factor experiments reveal complex responses, including acclimation in some taxa and heightened vulnerability in others. Ecosystem-level consequences may include altered competitive hierarchies and community restructuring. These interacting stressors underscore that ocean change rarely occurs in isolation. Rather, physical and chemical shifts intersect within living systems. The cumulative effect depends on resilience thresholds across trophic networks. The deep pelagic realm remains one of Earth's least sampled habitats, despite covering the majority of planetary surface area. Autonomous vehicles and environmental DNA analyses now reveal greater biodiversity than previously assumed. Many species remain undescribed, adapted to high pressure and limited food supply. Biological processes here operate on slower timescales, with growth and reproduction often prolonged. Exploration continues to refine understanding of carbon transport, species distribution, and ecosystem function. The deep pelagic zone embodies both scientific frontier and reservoir of unknown evolutionary innovation. Ocean atmosphere coupling governs monsoon systems and hurricane intensification. Warm sea surface temperatures provide latent heat energy fueling tropical cyclones. Vertical wind shear and ocean heat content influence storm development trajectories. Climate variability alters these parameters, potentially modifying storm frequency and intensity. The ocean acts as both energy source and thermal regulator, modulating atmospheric extremes. Observational networks monitor sea surface temperature anomalies to anticipate storm behavior. In this coupling, fluid dynamics of water and air interlock, shaping weather patterns affecting millions. Marine sediment burial permanently removes carbon from short-term cycling. Organic matter reaching the seafloor may become incorporated into sedimentary strata, eventually lithified into sedimentary rock. Over geological timescales, tectonic uplift and weathering reintroduce this carbon to the atmosphere. This slow geochemical cycle regulates atmospheric composition across millions of years. The ocean floor thus functions as long-term carbon archive, storing remnants of past productivity within stratified deposits. Burial efficiency depends on oxygen availability, sedimentation rate, and biological activity. Technological advances in deep-sea robotics enable prolonged observation without direct human presence. Remotely operated and autonomous vehicles survey hydrothermal vents, trenches, and abyssal plains with high-resolution imaging. Sensor arrays measure chemical flux, seismic activity, and biological behavior in situ. These tools extend observational reach beyond limitations of crude submersibles. Data integration across platforms enhances understanding of spatial and temporal variability. Exploration technology reshapes perception of the ocean from inaccessible void to instrumented environment. Ocean resilience depends on feedbacks between physical inertia and biological adaptability. While circulation patterns exhibit long response times, ecosystems can reorganize over shorter intervals. Migration, genetic adaptation, and community restructuring may buffer certain changes. However, thresholds exist beyond which recovery becomes uncertain. Adaptive management and reduction of anthropogenic stressors influence outcome trajectories. The ocean's future remains dynamic, contingent upon interplay between natural variability and sustained human influence. Theoretical projections of future oceans consider scenarios ranging from stabilized warming to continued greenhouse forcing. Models simulate shifts in circulation strength, stratification patterns, and biogeochemical cycling. Some scenarios anticipate poleward migration of biodiversity and expanded oligotrophic zones. Others explore potential tipping points within overturning circulation. Uncertainty persists, yet physical principles constrain possible pathways. The ocean will continue to absorb heat and carbon according to thermodynamic law, while life adapts within emergent boundaries. In contemplating centuries ahead, one confronts not a static destiny but an evolving equilibrium shaped by physics, chemistry, and collective human choice.